What do you do when the most distant machine humanity has ever built stops answering you? And the only way to fix it might take 3 days, just to find out if it worked. On a quiet afternoon in the summer of 2023, a spacecraft flying farther from Earth than anything else we have ever launched simply stopped talking. If this is the kind of story that makes your stomach tighten a little, hit like right now, tap subscribe, and send this to one person who loves a good real-life mystery, because this one is not fiction. And it gets stranger the deeper you go. Let's set the scene properly, because the scale of this story does not make sense until you understand exactly how far away we're talking about. Voyager 2 is a spacecraft the size of a small car, launched in August of 1977, back when calculators were still a novelty and nobody had heard of a home computer. It was sent out to do something no machine had ever attempted: fly past Jupiter, then Saturn, then Uranus, then Neptune, using the gravity of each planet like a slingshot to reach the next one. This exact alignment of the outer planets only happens once every 175 years. The engineers who designed this mission in the 1970s knew they had a single window in their lifetimes to pull it off, and they took it. Along the way, during that original grand tour, Voyager 2 did things no spacecraft had ever done before. It gave humanity our first close look at Uranus and Neptune, planets so far away that even today, decades later, no other mission has ever visited them again. It discovered new moons around these distant worlds. It found rings around Neptune that nobody had confirmed existed until that flyby. It measured wind speeds on Neptune faster than anything recorded anywhere else in the solar system. Every one of those discoveries came from a spacecraft that was only ever expected to survive long enough to finish that single tour and then quietly fade away. And yet, decades after that tour ended, engineers on Earth were still writing new instructions for it, still trusting a machine built with technology from a different century to carry out commands correctly, without ever once being able to physically check on it. Nobody expected Voyager 2 to still be flying decades later. The mission was built for about 5 years of active science, maybe a little more if the hardware held up. Instead, it kept going. It kept sending data home. It kept working long after every reasonable estimate said it should have gone dark. By 2018, it had been running for 41 years, and it did something only one other object in human history had ever done. It crossed the outer edge of our solar system, the boundary where the sun's influence finally gives way to the vast emptiness between the stars. We will come back to that moment, because what it found out there broke almost every prediction scientists had made. But first, we need to talk about the day it went quiet. Here's the constraint that makes this entire story almost unbearably tense. Radio signals travel at the speed of light. That is the fastest anything in this universe can move, full stop. And Voyager 2 is now so far from Earth that even light itself needs about 18.5 hours just to cross the distance one way. Send a message and you wait 18.5 hours for it to arrive. Then you wait another 18.5 hours to find out if anything happened. That is nearly a day and a half for a single round-trip conversation. There is no shortcut. There is no faster channel. The laws of physics do not make exceptions for anyone, not even for NASA engineers desperate for an answer. In the final days of July 2023, a team at NASA's Jet Propulsion Laboratory in California was sending a routine batch of scheduled commands to Voyager 2, the kind of maintenance instructions that had been sent successfully for decades without incident. Somewhere inside that sequence, something went wrong. A single mistaken command was transmitted, and its effect was small in numbers but devastating in consequence. The spacecraft's large dish antenna, the one piece of hardware responsible for both receiving instructions from Earth and sending all of its scientific data home, tilted 2 degrees away from where it was supposed to be pointing. 2 degrees does not sound like much. In almost any other context, a 2-degree error would barely register as a problem. But remember the distance we are talking about. Across more than 12 billion miles, a shift of 2 degrees is enormous. Earth, from where Voyager 2 sits, is an almost impossibly small target in the sky. The antenna has to aim with extreme precision to keep the connection alive. And a 2-degree drift was more than enough to break it completely. Just like that, the spacecraft could no longer hear anything sent from Earth, and Earth could no longer make sense of anything it sent back. The team at JPL was left in an almost impossible position. They needed to send a fix, but the fix itself had to travel through space to an antenna that was no longer pointed toward them. It was a bit like trying to shout instructions to someone wearing headphones that are now facing the wrong way. Except the person is over 12 billion miles away, and you cannot even confirm they are still listening. There were really only 2 paths forward. The first was to attempt an extremely powerful transmission from Earth, using the strongest ground stations available, and simply hope that enough of the signal would reach the misaligned antenna anyway. The mission's project manager was honest about the odds. She described the chance of success as low, not impossible, just low. The second option was patience. Voyager 2's onboard systems are programmed to automatically reset its orientation several times a year as a built-in safety measure. precisely for situations like this. The next scheduled reset was set for the middle of October. That was the guaranteed fix. But it was months away, and every single day between now and then meant losing data from a region of space that no other instrument on Earth had access to. Before attempting anything drastic, the team did something careful. Using multiple large radio dishes scattered around the globe, all listening together, they searched not for data, but simply for a pulse. A carrier signal is the most basic radio frequency any active spacecraft continuously broadcasts, a kind of electronic heartbeat that tells you the machine is still alive, even if it cannot say anything meaningful yet. On the first day of August, they found it faint. Weaker than normal because the antenna was still misaligned. But there, the spacecraft was alive. It simply could not talk properly. Think about what that search actually required. Multiple giant dishes on opposite sides of the planet, all pointed at the exact same tiny patch of sky, straining to catch a whisper of radio energy so faint that it barely rose above the natural static of the universe itself. There was no guarantee they would find anything at all. If the antenna misalignment had been caused by something more serious than orientation, a genuine hardware failure deep inside the spacecraft, there might have been nothing to hear, no matter how hard anyone listened. Every second of that search carried the quiet possibility that the mission was already over and that nobody on Earth would even know it yet. The engineers running that search had spent entire careers around this spacecraft, and even they could not tell you in that moment whether they were listening for a survivor or confirming a loss. That uncertainty is not something you get used to. It is something you sit inside hour after hour while the rest of the world goes about its day with no idea any of this is happening at all. That heartbeat changed everything about the plan. If a whisper that faint could still be detected from 12 billion miles away, then maybe, just maybe, a powerful enough shout from Earth could reach the antenna even while it was pointed the wrong way. On the 2nd of August, the team made the attempt. A massive radio dish in the southern hemisphere, chosen specifically because its geometry lined up best with Voyager 2's current position, fired an enormously powerful signal straight at the spacecraft's last known coordinates. The instruction packed into that signal was simple. Turn the antenna back toward home. And then the waiting began. 18 and a half hours for the message to arrive, assuming it arrived at all. Then, if everything worked, another 18 and a half hours for any kind of response to travel back across the void. 37 hours total, minimum, before anyone on Earth would know whether this desperate long shot had worked, or whether the spacecraft would remain silent until October. Try to imagine sitting in that control room. You have sent your one best attempt. You cannot check on it. You cannot send a follow-up question. You cannot do anything except wait and hope that somewhere out past the orbit of every planet, in the cold, dark space between stars, a 46-year-old antenna heard you and decided to turn around. If a story like this has you leaning forward right now, that is exactly the kind of curiosity this channel lives for. Smash that like button, subscribe if you have not already, and let us keep going, because the moment the answer finally came back, changed the entire tone of the story. At 12:29 in the morning, Eastern Time, on the 4th of August, 2023, 37 hours after that desperate transmission was sent, something happened on the screens at Mission Control. Data started flowing again, not garbled, not partial. Real, structured, readable telemetry, exactly the kind Voyager 2 had been sending home every single day since 1977. The antenna had turned, the spacecraft had heard the shout across 12 billion miles of empty space, and it had obeyed. People who were in the room that night described the reaction as pure, unguarded relief, the kind that only comes after days of sitting with a real possibility of permanent loss. The project manager later said something that stuck with a lot of people who follow this mission closely. She said that after decades of working with these old spacecraft, engineers developed something like a real relationship with them. And having Voyager 2 talking again felt like getting a member of the team back. 14 days. That is how long the total silence lasted, from the moment the wrong command was sent to the moment full communication was restored. 14 days is the longest gap in contact in the entire 46-year history of this mission. And here is the detail that makes those 14 days matter far beyond the drama of the recovery itself. Voyager 2 is not just an old machine limping along for sentimental reasons. It is, right now, the only spacecraft humanity has ever operated south of our solar system's equatorial plane, out in true interstellar space. If those 14 days had stretched into permanent silence, we would not simply be losing a machine. We would be losing our only working eyes and ears in a region of the universe that no telescope, no computer model, and no theory built entirely from Earth has ever managed to describe correctly in advance. Because here's the thing nobody expected. When Voyager 2 finally crossed the true edge of our solar system, Back in November of 2018, becoming only the second human-made object ever to do so, what it found out there did not match what scientists had spent decades predicting. And unlike its twin, Voyager 1, which had crossed the same kind of boundary 6 years earlier with a broken plasma instrument, Voyager 2 crossed with every relevant sensor still working. For the first time ever, scientists had a direct, real-time measurement of what actually happens at the boundary between our solar system and the rest of the galaxy, taken by an instrument physically passing through it. The results were strange enough that 5 separate research teams published 5 separate papers about them on the exact same day, a full year after the crossing, once the data had been fully analyzed, and almost none of what they found matched the textbook expectations. To really appreciate how strange these findings were, you have to understand what scientists thought they already knew before Voyager 2 ever arrived. For decades, our picture of the Heliopause was built almost entirely from indirect clues. Telescopes on Earth and in orbit had studied the general glow of energetic particles coming from that direction. Earlier spacecraft had measured related but incomplete pieces of the puzzle. Researchers built increasingly detailed computer models, trying to stitch all of these clues together into a coherent picture of what the boundary should look like, how thick it should be, how it should behave. These models were taken seriously. They were published in respected journals and taught in university courses. And when the actual data came back from a spacecraft physically sitting inside the boundary itself, several of those carefully built assumptions did not hold up. Scientists had long assumed the edge of our solar system, called the Heliopause, would be a slow, gradual fade. Solar wind particles thinning out bit by bit, interstellar particles slowly mixing in, over a wide stretch of space that might take weeks to fully cross. What Voyager 2 actually measured was nothing like that. The transition happened in less than a single day of travel time. One environment on one side, a completely different environment on the other, separated by a boundary so sharp it barely deserved to be called a boundary at all. It was closer to a wall. The temperature of the plasma just outside that wall was another shock. Models had predicted interstellar plasma near this boundary would be cold, matching the general expectation that the space between stars is a frozen, quiet place. Voyager 2's instruments measured something noticeably warmer than anyone had predicted. This was not a small rounding error in a calculation. It was a real measured difference between what the model said should be there and what was actually there, recorded directly by a machine sitting in the middle of it. Then came the magnetic field data, which turned out to be its own kind of surprise. Just inside the Heliopause, Voyager 2's instruments detected something researchers began calling a magnetic barrier, a narrow region where the strength of the magnetic field spiked sharply before settling back down. This barrier appears to play a major role in controlling how cosmic rays, high-energy particles blasted out by distant exploding stars across the galaxy, are allowed to enter our solar system. Scientists already knew the heliosphere offers some protection from these particles. What they did not know, until Voyager 2 sent the data home, was just how structured and specific that shielding mechanism actually is. None of these 3 findings, the sharpness of the boundary, the unexpected warmth of the plasma, and the structure of the magnetic barrier, existed as serious possibilities in the scientific literature before Voyager 2 crossed. They emerged directly from data collected by an instrument that almost did not survive long enough to make the crossing at all. If that plasma science instrument had failed the way its counterpart on Voyager 1 had failed years earlier, none of this would have been measurable. Scientists would still be relying entirely on models and comparisons, still guessing at a boundary they had never actually touched with working instruments. If you're the kind of person who finds real, hard, ground truth data more thrilling than any fictional plot twist, you are exactly who this channel is made for. Ring the notification bell, drop a comment telling me which detail surprised you the most so far, and let's keep pushing into the deepest part of this story. Before Voyager 2 ever reached this boundary, most predictions about it came from computer models built using indirect evidence, mathematical extrapolation, and educated guesswork based on observations of other stars from enormous distances. Nobody had ever been able to check those models against real, direct measurements taken from inside the boundary itself. That is what makes this story so different from ordinary planetary exploration. When a probe flies past a planet, scientists can usually predict a great deal about what it will find, because telescopes on Earth have already studied that planet for generations. Nobody has ever been able to point a telescope at the exact structure of the Heliopause and see it clearly enough to test these predictions in advance. Voyager 2 was not confirming a known picture. It was replacing one. There is one more layer to the Heliopause story that deserves real attention, because it completely reshapes how scientists think about the shape of our own solar system. Voyager 1 and Voyager 2 did not cross this boundary at the same location. Voyager 1 crossed heading north above the Sun's equatorial plane. Voyager 2 crossed heading south below it. If the bubble surrounding our solar system were a perfect sphere, uniform in every direction, both spacecraft should have found essentially identical conditions at their respective crossings. They did not. Voyager 2 found a thinner boundary. It found stronger magnetic fields. It found plasma conditions measurably different from whatever Voyager 1 had recorded years earlier at its own crossing point. This tells scientists something significant. The bubble that surrounds our entire solar system, the one that shields every planet, every moon, and every living thing from the harsher radiation of deep space, is not symmetrical. It is compressed in some directions and stretched out in others, shaped by its ongoing collision with surrounding interstellar material. Two spacecraft crossing at two different points gave scientists their first two real data points describing a shape that no model, before either crossing happened, had gotten quite right. Picture our solar system not as a perfect ball floating peacefully in empty space, but as something closer to a comet moving through a thin haze, pushing harder against the material in front of it while trailing a longer, thinner tail behind. That is closer to the emerging picture. Scientists are now building, piece by piece, using exactly two direct measurements taken 46 years, into a mission nobody expected to last this long. This is exactly why the near loss of Voyager 2 in the summer of 2023 mattered so much more than a simple mechanical glitch. The spacecraft, running on hardware from the disco era, holding onto a slowly decaying trickle of power, is still the only instrument humanity has ever operated in that particular region of interstellar space. No replacement mission exists. Nothing is currently on a trajectory to reach that same boundary from that same direction any time in the coming decades. If the antenna problem had gone unresolved, that specific scientific vantage point, unique among everything humanity has ever built, would have been gone permanently. It is worth appreciating, for a moment, the sheer engineering effort required just to make that rescue attempt possible in the first place. The ground stations capable of reaching a spacecraft this far away are part of a global network of giant radio dishes positioned at 3 different points around planet Earth, spaced deliberately so that at least one station always has a clear line of sight toward deep space. As Earth turns on its axis, the network never fully loses contact with the outer solar system. Each site contains multiple dish antennas, the largest of which stretch about 70 meters across, among the most sensitive radio receivers ever constructed by human beings. They are capable of detecting signals so faint they barely qualify as a whisper, and focused enough to pinpoint an object moving tens of thousands of miles an hour from over 12 billion miles away. Consider what it actually takes to run a network like this day after day, year after year for nearly half a century. These are not machines you switch on once and leave alone. They require constant maintenance, careful calibration, and teams of engineers working in shifts around the clock, because deep space does not observe business hours. A signal from Voyager 2 might arrive at 3 in the morning local time at one of these stations, and someone has to be there, ready, paying attention, because a missed window cannot simply be repeated an hour later. The spacecraft will not wait. It keeps moving, keeps transmitting on its own schedule. The particular station used to send that desperate command in August 2023 was chosen for a very specific reason. Voyager 2 is heading south relative to our solar system's equatorial plane, and the station in the southern hemisphere had the best geometric alignment. A signal generated by a dish on Earth, aimed with extraordinary precision, crossed the entirety of interstellar space and reached a machine barely bigger than a compact car. That such a thing is even physically achievable tells you as much about the nature of radio waves as it does about human engineering. Radio waves do not fade the way sound does in air. They spread outward, weakening with the square of the distance traveled, which means that by the time the signal reached Voyager 2, it had grown extraordinarily faint. But faint enough was still enough. The antenna, even misaligned, still caught it. Take a second to notice how many things had to go exactly right here. The signal had to be strong enough to survive 12 billion miles of empty space. It had to arrive at precisely the right angle to be caught by a dish tilted 2 degrees off target. The spacecraft's decades-old onboard systems had to correctly interpret the instruction and physically move a mechanical component. And all of that had to happen without a single opportunity for anyone on Earth to check in, correct a mistake, or offer any kind of guidance. It worked, but it very easily might not have. It is worth asking why any of this matters beyond pure curiosity, because the answer connects directly to questions much closer to home. The same magnetic barrier and cosmic ray shielding that Voyager 2 measured at the edge of our solar system plays a direct role in protecting every living thing inside it, including us, from a constant rain of high-energy radiation. Understanding exactly how that shielding works, how strong it is and where it is weaker, matters for anything humanity ever hopes to do beyond Earth. Long-duration crewed missions, future outposts on the Moon or Mars, even our understanding of how life manages to survive at all on a small rocky planet, depends on understanding the bubble that surrounds us. Voyager 2 is not just measuring an abstract, distant boundary. It is measuring the outer wall of the only safe room our species has ever known. There is also a broader scientific stake here that goes beyond our own solar system entirely. Astronomers studying stars across the galaxy increasingly believe that many other stars likely have their own version of a heliosphere. Voyager 2's direct measurements give scientists actual, real numbers to test against the models used to predict what those other bubbles look like. This single-aging spacecraft is quietly helping researchers understand not just our own solar system, but the basic physics of how stars across the entire galaxy interact with the vast ocean of gas and plasma drifting between them. This story deserves one more comparison because it puts the stakes into sharper focus. A few months after Voyager 2's antenna crisis, its twin spacecraft, Voyager 1, experienced its own separate and even more serious problem. A memory chip inside its onboard computer system began malfunctioning, causing the spacecraft to transmit garbled, unreadable data for 5 months straight. That crisis was fundamentally different from Voyager 2's antenna misalignment. This was not a simple orientation problem. This was internal hardware, slowly failing, forcing engineers to find a way to route around a piece of physical memory that no longer worked, using programming methods from an era before most of them were even born, all while communicating across a delay of 22 hours each way. Both crises shared the exact same underlying pressure. Every single decision carried the weight of permanence. There is no repair crew that can be dispatched. There is no way to physically inspect a component. There is no safety net beyond careful thinking and educated guessing based on decades-old blueprints. And in both cases, against genuinely low odds, the team succeeded. Both spacecraft came back online. Both recoveries left behind a sobering realization that the window for gathering this kind of data is finite, it is shrinking, and once it closes, there is no reopening it. There is something almost poetic about who is doing this work today. Voyager 2 was built by engineers who are now in their 70s and 80s. Some of them are no longer alive to see how far their creation has traveled. The people maintaining it today were mostly not even born when it launched. They have inherited a machine, its quirks, its history, and the enormous responsibility of keeping it alive using instruction sets and computer languages already outdated. When something breaks out there is no manual written for that exact situation. There is only careful reasoning, creative problem solving, and total awareness that a single wrong command sent across billions of miles cannot simply be undone. There is a particular kind of humility built into this job that is worth pausing on. Every engineer who works on Voyager 2 today knows they did not build it. They inherited it the way you might inherit a family home built by grandparents you never met, full of quirks and wiring choices that made perfect sense then but require real detective work to understand today. They study old technical drawings. They keep a physical replica of hardware in a lab, so they can test a risky command first before ever sending it to the real thing. There is no substitute for that kind of caution when a single mistake cannot be taken back. If this kind of quiet, human dedication behind the scenes of space exploration moves you even a little, that is worth acknowledging. Share this video with someone who still gets excited about real space stories, hit subscribe, and let's keep going. Voyager 2's power supply comes from the slow, steady decay of plutonium inside its onboard generator, a process that has been quietly ticking away since before most of the people reading this were born. Every single year, it produces a little less electricity than the year before, losing roughly 4 watts of available power annually. That might not sound like much, but 4 watts a year adds up relentlessly over decades, and there is no way to refuel it. Engineers have had to make increasingly difficult choices, shutting down individual scientific instruments one at a time to keep enough power flowing. Each shutdown is permanent. There's no switching an instrument back on once its power has been redirected elsewhere. Every decision to turn something off is really a decision about what kind of data humanity is willing to live without for the rest of this mission. And that lifespan is not indefinite. At some point, likely in the early 2030s, the available power will drop below whatever threshold is needed. And the signal, the one that has been arriving reliably at ground stations on Earth for nearly half a century, will simply stop. When that day comes, it is unlikely to make headlines outside the community of people who have spent their careers studying this exact spacecraft. But within the small circle of scientists who study the boundary of our solar system, the end of Voyager 2's transmissions will close a window. It took 46 years to open, and one that cannot be reopened again on any timeline that matters to anyone currently working in this field. No mission is currently funded to replace it. No spacecraft is currently traveling toward that same region from that same angle. Whatever we learn between now and the day the signal finally stops is all we are ever going to learn directly from that corner of the universe in our lifetimes. If you have made it this far into the story, you clearly care about the kind of quiet, patient discovery that does not always make the front page. Tap like, and if a notification bell is available to you, turn it on, because the next chapter of this mission is coming eventually. Somewhere in the coming decade, a final message will arrive at one of those giant dishes on Earth, and it will be the last one. There will be no dramatic announcement, because nobody will know for certain that it is the last one until enough silence has passed. There will be no dramatic countdown, no final broadcast, no clean and cinematic goodbye. Just a gap in the data that stretches a little longer than usual, until the people watching those screens finally allow themselves to accept what the silence is telling them. Engineers will keep listening for a while after, the same way you might keep checking your phone after a loved one stops replying, hoping the silence is temporary, hoping there is still a chance. At some point, that hope will quietly give way to acceptance, and the mission will truly end. Even after the power runs out and the final signal fades into silence, Voyager 2 itself does not stop. It does not fall. It does not crash. There's nothing out there to crash into. It simply keeps moving silently in a straight line, carrying with it a golden record. That record holds greetings recorded in dozens of languages and pieces of music from cultures all across our planet. It was assembled by people who understood that this machine might genuinely outlast our entire species, and who wanted to leave behind something honest in case anything or anyone out there ever finds it. The golden record itself is a strange and beautiful object. It contains images encoded in analog form showing our planet, our bodies, and our cities. It contains greetings spoken aloud by ordinary people who had no idea their voice might outlast every structure ever built by humankind. It contains music meant to say something true about what it feels like to be a living, feeling creature on this particular planet. Nobody who worked on that record expected it would ever actually be found. It was never really about being found. It was about the act of trying. Voyager 2 will keep traveling long after every engineer who ever worked on it is gone, long after the antennas that once shouted across 12 billion miles of space have been replaced by newer technology we cannot yet imagine. It will keep moving through the same interstellar plasma it is measuring right now, carrying a message from a civilization that built something durable. Think about the sheer improbability of everything that had to happen just for you to be hearing this story right now. A specific alignment of planets once every 175 years. A spacecraft built with hardware never expected to last this long. A 2-degree antenna error corrected by a shout fired across 12 billion miles of empty space, based on a hunch that a heartbeat meant a shout might land. Every single link in that chain had to hold. If even one of them had failed, this story would have ended quietly. Right now, today, as you are watching this, it is still out there, still transmitting, still sending back numbers and readings. From a region of space that every model built before it arrived described incorrectly in some meaningful way.